Welcome to Debug Log, software engineering war stories, architecture decisions, and lessons learned the hard way. Let's dig in. The promise of Retrieval Augmented Generation, or RAG, in AI coding agents often sounds like a silver bullet for developers. Feed it documentation and it should just know how to fix things, right?
That's the theory. But a recent examination into what happens when AI coding agents are tasked with fixing actual Kubernetes bugs paints a rather sobering picture. It suggests that the RAG setup, while conceptually sound, isn't the panacea many assume for complex, real-world systems.
So the delusion part of this, then, is the overestimation of RAG's current capabilities in truly difficult, enterprise-grade software environments. That it's not enough to just give it the manual?
Precisely. The core finding is that even with extensive, relevant documentation fed directly to them via RAG, these agents still struggle significantly with the nuanced, interconnected challenges found in complex systems like Kubernetes. The problem isn't necessarily a lack of information, but a deficiency in interpreting and applying it effectively.
To elaborate on that, what exactly is RAG in the context of an AI coding agent, and why is it seen as such a critical component for these tools?
At its simplest, Retrieval Augmented Generation combines a large language model with a retrieval system. Instead of the LLM relying solely on its internal pre-trained knowledge, the retrieval component pulls relevant documents, like API specifications, technical manuals, or even past bug reports, from a knowledge base. This retrieved context is then fed to the LLM alongside the user's query, theoretically allowing the LLM to generate more accurate, grounded responses.
So the idea is to prevent hallucination and keep the AI on topic with current, specific information, rather than general knowledge it might have picked up during training. For coding agents, this means giving it access to all the official documentation for the frameworks or libraries it's working with.
Exactly. You'd expect that if an agent has access to the Kubernetes API docs, example configurations, and official troubleshooting guides, it should be able to diagnose and propose fixes for Kubernetes-related issues. It's supposed to bridge the gap between general language understanding and domain-specific technical expertise.
But the paper suggests this bridge isn't as robust as one might hope, especially for the 9 Kubernetes bugs they examined. What kind of bugs were these, and why were they chosen as a testbed?
These weren't trivial syntax errors or simple misconfigurations. The bugs chosen were known, real-world issues within Kubernetes that required a deep understanding of its distributed architecture, resource management, and intercomponent communication. Think subtle race conditions, complex networking policy interactions, or issues arising from resource contention in a multi-tenant environment. They were selected because they represent the kind of intricate problem-solving that human SREs and developers regularly face.
So not, my pod didn't start because of a typo, but my pod didn't start because of a very specific cascading failure mode involving a webhook, a mutating admission controller, and an obscure network plugin interaction.
A very apt analogy. These bugs demand not just knowledge of individual components, but an understanding of their dynamic interplay and the system's overall state. The chosen bugs are representative of the kind of problem where a human engineer would spend hours, possibly days, tracing execution paths and correlating logs across multiple services. It's a high bar for any automated system.
And how did the RAG-powered agents fare against these complex challenges? Where did they fall short specifically?
The agents frequently failed to synthesize information from disparate sources. They might retrieve relevant individual documents, say the API specification for a particular resource and a troubleshooting guide about a related component, but then struggle to connect the dots between them. It's like having all the pieces of a puzzle but no understanding of the picture they form.
So it's not a retrieval problem, but a reasoning problem? The information is there, but the AI can't build a coherent, actionable mental model from it?
That appears to be a significant part of it. The agents also exhibited difficulties with contextual understanding. For instance, they might correctly identify a symptom, but then propose a fix that addresses a superficial aspect rather than the underlying root cause, or a solution that would create new problems elsewhere in the distributed system. This highlights a critical gap in their ability to grasp the broader system implications of a proposed change.
That sounds a lot like a junior developer who knows the syntax but doesn't quite grasp the architectural implications of their code. They can retrieve information on individual functions, but struggle with how those functions fit into a larger, dynamic system.
An accurate parallel. Another common failure mode was an inability to engage in multi-step iterative debugging. Real-world debugging often involves hypothesizing, testing that hypothesis, observing the outcome, refining the hypothesis, and repeating. The agents often struggled to follow this iterative loop effectively, sometimes getting stuck on an initial incorrect assumption or failing to properly interpret diagnostic output.
So the AI might suggest a command to run, but then not know what to do with the output of that command, or not connect it back to its original hypothesis about the bug?
Precisely. It lacks the internal feedback loop and adaptive reasoning that a human engineer uses. It's not just about querying for information, it's about forming a mental model of the system's state, predicting behavior, and adjusting that model based on new evidence. This higher-order cognitive process seems to be a current limitation.
This raises a fundamental question about the nature of intelligence in these systems. Is it that the models lack the ability to reason in this way, or that their current training and RAG mechanisms don't adequately facilitate it?
The study strongly suggests it's a limitation in their reasoning and abstraction capabilities, at least with current architectures. While RAG provides the necessary information, it doesn't imbue the model with the human capacity for causal inference, abstraction beyond immediate context, or the ability to weigh trade-offs in a complex dynamic environment. Kubernetes, by its very nature, is an exercise in distributed systems trade-offs.
So even if the RAG system retrieves a document detailing a known issue with kubeproxy and another about network policies, the agent might still fail to connect these pieces to diagnose a specific pod connectivity problem caused by a misconfigured policy interacting with the proxy's IPVS mode. It's about more than just finding keywords.
It absolutely is. It's about understanding the relationships between those keywords, the causal chain of events that leads to a particular symptom, and the implications of modifying one part of that chain. Humans perform this synthesis almost unconsciously, drawing on vast amounts of implicit knowledge and experience. For AI, that level of nuanced understanding in highly specialized domains is still a significant hurdle.
This raises questions about the broader implications for AI agent development. If RAG isn't the magic bullet, what does this reveal about how these coding agents should be built or conceptualized?
It emphasizes that pure automation, especially for complex debugging tasks in critical infrastructure, is still a distant goal. The study reinforces the idea that current AI agents are most effective as assistants rather than autonomous problem solvers. They can help retrieve information faster, summarize logs, or even propose initial hypotheses, but they require significant human oversight and validation.
So instead of expecting an AI to just fix the bug, it should be considered a very sophisticated search engine and suggestion box that still needs an expert human in the loop to interpret, validate, and ultimately implement.
That's a more pragmatic view. It suggests that future improvements might not just come from bigger models or better retrieval mechanisms, but from developing AI systems that can articulate their uncertainties, explain their reasoning steps, or ask clarifying questions in a more intelligent way. Essentially, becoming better collaborators rather than attempting full autonomy where they are currently outmatched.
It also highlights the continued value of human expertise in navigating these labyrinthine systems. The ability to form high-level abstractions, to intuit subtle interactions, and to apply domain-specific wisdom gathered over years, those capabilities remain firmly in the human domain for now.
Indeed. The study underscores that while AI can process information at scale, it's the wisdom derived from experience and deep contextual understanding that allows humans to truly debug and architect complex systems like Kubernetes. It's a reminder that complexity often requires more than just access to data. It requires understanding.
This journey through the RAG delusion in Kubernetes bugs provides some critical insights. First, the simple act of providing an AI agent with comprehensive documentation via RAG is not sufficient for it to effectively diagnose and resolve complex real-world software bugs.
Second, current AI agents struggle significantly with abstract reasoning, synthesizing information from disparate sources into a coherent causal model, and engaging in multi-step iterative debugging processes, particularly within highly interconnected and distributed systems.
Third, the limitations observed are not merely about a lack of data, but rather deficiencies in the AI's ability to interpret context, understand system-wide implications, and perform the kind of nuanced problem-solving that human engineers routinely employ.
Finally, these findings suggest a more realistic path forward for AI and software development as powerful assistants that augment human capabilities in information retrieval and hypothesis generation, rather than fully autonomous agents capable of independent, complex debugging in critical infrastructure.
So, for listeners thinking about integrating AI coding agents into their workflows, the practical implication is that human expertise and oversight will remain indispensable, especially for high-stakes, intricate problems. It's about leveraging AI for speed and information access, but retaining human judgment for architectural integrity and root cause analysis.
A crucial distinction. The question then becomes, how should these systems be designed to best leverage AI's strengths while continuously developing and valuing the irreplaceable human capacity for truly complex problem-solving?
And how can it be ensured that the convenience of AI doesn't lead to a degradation of fundamental debugging skills among human developers if they become too reliant on tools that don't always grasp the deeper context?
That's a wrap on this debug log. Join us next time for more engineering war stories and hard-won lessons. If any of this hit close to home, subscribe and tell your team.
Ship it carefully.